All right, let's jump right into how we act as chemical detectives. Today, we're decoding unknown substances using analytical chemistry. Think of it like a CSI investigation. Whether we're testing drinking water for contaminants or analyzing evidence at a crime scene, we use chemical reagents instead of fingerprints to unmask mysterious metal ions that are hiding right there in plain sight.
Here is what we're covering in this explainer. First, an intro to analytical chemistry. Then, sodium hydroxide reaction tests, followed by ammonium hydroxide tests. After that, alkali reactions with metals. And finally, the magic amphoteric oxides. Let's get to it. Section 1. Intro to Analytical Chemistry. So the crucial thing to remember here is that we are conducting qualitative analysis. We are entirely focused on the what, identifying the unknown substance itself. We don't really care about the how much, which would be quantitative analysis. And how exactly do we find out the what? Well, by carrying out chemical tests using specific substances called reagents and just watching for the visible changes. Our very first set of clues? Color. Before we even add a single drop of a chemical reagent, the natural color of a salt solution tells us a huge story. The salts of representative elements, groups 1, 2, and 13 to 17, usually give us perfectly colorless ions. But transition metals, those elements right in the middle from groups 3 to 12, they give us beautifully distinct, vibrant colors. Think about how identifying a specific color instantly narrows down our suspect list. See a pale blue solution? You're probably looking at cupric or copper-2 ions. A light green liquid? That's going to be your ferrous or iron-2 ion. Yellowish brown points us straight to ferric, iron 3. Meanwhile, cations like calcium, zinc, and lead, they just hide in plain sight as completely colorless solutions. Moving on to Section 2, sodium hydroxide reaction tests. Okay, so when we take our unknown salt solution and add an alkali like sodium hydroxide, and this is absolutely crucial, we do it drop by drop, we're watching closely for precipitation. This is that magical moment when an insoluble solid just forms out of two liquids. The color of this newly formed solid, the precipitate, is the key that will unmask our hidden metal ion. Let's map out our baseline rules here and understand exactly which vivid, insoluble precipitates form when we test our standard suspects. Calcium gives us a sparingly soluble white precipitate. Iron 2 forms a very distinct, kind of dirty green solid. Iron 3 drops out as a reddish-brown solid, and copper 2 reveals itself with a pale blue precipitate. And the neat thing, if you add excess sodium hydroxide to these, they stay exactly as they are, completely insoluble. Now, what's really fascinating is the exception to the rule. Both zinc and lead are our tricksters. If you add sodium hydroxide drop by drop, they both give you a white precipitate. That might make you think you have calcium, right? But here's the detective's secret. If you keep pouring and add excess sodium hydroxide, that white precipitate completely vanishes. It dissolves into a perfectly clear colorless soluble complex, specifically sodium zincate or sodium plumbite. And before we finish up with sodium hydroxide, we absolutely can't forget our nonmetal suspect, the ammonium ion. If you heat an ammonium salt with sodium hydroxide, you won't get a colorful precipitate. Instead, it undergoes a reaction that releases a telltale, super pungent gas, ammonia. It's a highly specific reaction that confirms the presence of the ammonium ion for sure. Section 3. Ammonium hydroxide reaction tests. Our first major difference happens right out of the gate with calcium. Remember how it formed a white solid with our last reagent? Well, because ammonium hydroxide is a weak alkali, it has a much lower concentration of hydroxide ions. It entirely fails to precipitate calcium. The solution just stays perfectly clear. This gives us a brilliant, foolproof way to distinguish calcium from our other suspects. Iron and lead, on the other hand, don't change their tune at all here. They lock into insoluble precipitates exactly like they did with our strong alkali. Iron 2 still gives us that dirty green, iron 3 gives us reddish-brown, and lead provides a chalky white precipitate. And importantly, even if you flood the test tube with excess ammonium hydroxide, these solids stubbornly refuse to dissolve. But get ready for the dramatic reveal for copper. When you add ammonium hydroxide dropwise, copper forms that familiar pale blue precipitate. But keep adding excess reagent, and something amazing happens. The pale blue solid suddenly dissolves, completely vanishing to create this stunning, deep ink blue solution. This soluble complex, tetramine copper-2 sulfate, is a definitive, unmistakable fingerprint for the copper-2 ion. And you know what? Zinc pulls a very similar disappearing act. It starts out as a gelatinous white clump when the reagent is added drop by drop. But just like copper, once you introduce excess ammonium hydroxide, that white solid dissolves entirely, leaving you with a perfectly clear, colorless solution of tetramine zinc 2 sulfate.
All right, Section 4, alkali reactions with metals.
So most metals don't actually react with alkalis at all. But zinc, aluminum, and lead, they're specific chemical rule breakers. If you expose them to hot, highly concentrated caustic alkalis, like sodium hydroxide or potassium hydroxide, they react violently. They form a soluble salt and, crucially, they bubble up and liberate hydrogen gas. When you break down the exact chemical equations for this process, you'll see zinc reacting with boiling sodium hydroxide to transform into a colorless solution of sodium zincate, all while bubbling away that hydrogen gas. Aluminum forms sodium meta-aluminate, and lead forms sodium plumbite. It's a really unique characteristic shared only by this specific trio of metals.
Finally, Section 5, the magic amphoteric oxides.
As a general rule in chemistry, metallic oxides are basic, meaning they dissolve in acids to form salts in water, but they simply ignore other bases or alkalis. But amphoteric oxides and hydroxides are literal chemical double agents. They possess a dual character, meaning they will actually react and neutralize both acids and alkalis to form salt and water.
To see this dual personality in action, zinc oxide can act like a typical basic metal oxide, reacting with hydrochloric acid to form zinc chloride and water. But then it can just flip its identity. It can act like an acid, reacting with the strong alkali sodium hydroxide to form sodium zincate and water. It's pretty wild.
Zinc, aluminum, and lead are the primary amphoteric offenders you're going to encounter. Whether they're in their oxide or hydroxide forms, these three elements simply refuse to follow the standard rules. They show both acidic and basic characteristics depending entirely on what you mix them with. We can trace exactly how each of these three metals balances perfectly between acidic and basic behaviors. Aluminum oxide forms sodium meta-aluminate with an alkali, while lead oxide forms sodium plumbite. They seamlessly adapt to their chemical environment to form these unique soluble salts.
So, let's put it all together. If you have a colorless solution that forms a white gelatinous precipitate with dilute ammonia, only to completely vanish in excess reagent, well, you know our slippery suspect is zinc. But this isn't just lab trivia, guys. These exact same chemical fingerprints are used every single day to test our drinking water, develop new medicines, and decode the materials all around us. So the next time you look at a perfectly clear liquid, ask yourself, what chemical secrets are hiding just a drop of reagent away?